only used for branching the condition, and plus leaf node at the children pointer. Let's see. We are going to use the exactly same thing, same sequence. It also has the in case of full, split, and promotion. It's the same thing. So first, A is inserted. The first data. Which one will be created? Leaf node or internal node? The first node. Which one will be?
Leaf node.
Leaf node, because we have only one node, so we don't have to branch. So we don't need the internal node. Only this one will be inserted. Then, which one? So A. How many? So up to 2. The P leaf means that we can have the 2 index key entry. So still available. This pointer, actual point, data pointer, data block pointer. Okay? Then, so far so good. What about the 5? We have space. 5 is inserted, we can sort 5 and 8, and this is a data pointer. I'm going to skip the data pointer part. So that's it. I don't explain this one. We don't use yet. Then the problem is same as this one. 1 is inserted. What happened? It's a full. In case of full, 1, 5, 8, we need to split. Split into 2 groups. Decide the middle value, just like the B3. Then this is different. So we can split into 2. Split means exactly same copy. Let me make this space. Okay. Here, because we split left-hand side, right-hand side, and middle value is promoted. Because of this one, middle value still keep the data pointer. So in B plus 3, we keep middle value and left-hand side into the left-hand side, 1, 5, including middle value. Right-hand side, bigger than the middle value, right-hand side. Okay? Then, without promotion, we just use the middle value for internal load. So internal load is not this one. Internal load has the only children pointer. Then 5 will be used for branching condition. Then equal or less than. Equal or less. This is different. That is less than, but here equal or less than 5 goes to here. These children. And bigger than 5 goes to here. Does it has the data pointer? No data pointer. It will be used for only condition for branching. Split into 2. Okay, then here just the pause to proceed. When I access the 5, like the select asterisk from student, where ID is equal to 5. How many IO do we need? How many IOs? How many IOs? 2? 3?
5 of them.
First, you need to visit the root node. Is there any 5? No 5. 5 means ID, index ID. 5. This is just for branching purpose. Equal or less than 5 goes to here. Then 5 has the data pointer. Then using this one, access the data 5. How many are you? 1, 2, 3. What about 8? 1, 2, 8. The 3. What about 1? 1, 2, 3. Always 3. Level plus 1. It's a fully balanced. That's the difference. Don't be confused. There's no data pointer. It's only used for the So it's a copy of the middle value and used for the branching. Okay, then continue. So after 1, it will be 7. What if 7 is inserted? 7, can we use this one? No, you need to find the available index key entry. 7 is bigger than 5, goes to here, so 7 will be inserted. I forgot one thing, this one. This is different from the B3 index. This is called sibling pointer. They are, both of them are children of this, right? This is a sibling. Their relationship is a sibling in the same level. So the sibling pointer point to the next sibling node. Okay, yes, question.
If 6 is coming next number, so where will we insert?
We will see in the keep next. We will see. Okay, principle. First, explain about this one. This is a sibling pointer. That's different from here. What is the benefit of the sibling pointer?
If I need immediate next data.
Next data. That means range search. For example, let's suppose that we have the query select from student where ID is like this one. What about using B3 index? You need to find first 1 and read the data. Then next one is here. The 3, read the data. What about the 5? You need to go up and read the data, and next down, up and down. Traverse. You learn how to traverse the graph. And tree. The tree, one of the problem of the tree is it should be up and down, up and down, up and down to read the data. You can sort the data using binary search tree. But the traverse is from left to right and up and down. That is the problem. What about this one? Once you find this one, 1, 5. Because all data node, key entry is a leaf node. You can just use sibling pointer. You don't have to going up. So this B plus 3 is very good for range query. Okay. A lot the benefit using sibling pointer. So sibling pointer is another different from the B3 index. Okay, we move to the next one. So we did 7, 3. So what if 3 is inserted? Can I insert the 3 here? No, this is only for the branching. So we need to, 3 is less than 5 and supposed to be here, it's a full. So we need to decide the middle value. Which one is the middle value? 3. Then this will be equal or less than the middle value left hand side bigger than right hand side. Which means we need to copy and 1, 3, 5. Okay, then 3 will be used for here. There is a space, so we can 3 and 5. Then we organize equal or less than, always equal or less. That's different from the B3. And bigger than 3, equal or less than 5 here. This. It's not done yet. We need to sibling point. Okay. Then next, 3 is done. 12. If 12 is inserted, supposed to be here, right? What is the full? 7, 8, 12. This one middle. 7 and 8 left hand side, right hand side. So 7 and 8. Oops. This is from my old university. Okay, then 7 and 8 12. Then 8 will be here. What happened? It's a full. You cannot use the 12 here because only 2 of you can use the same algorithm, split and promotion used in the big tree here. So let's do. This is the most the confused part. Which node we need to use? This one or this one? Internal node. Because leaf node is only this, and the other internal node will use this one. So we can copy to and promotion. Okay. Which one will be here? 8. That's good. What about this one? Left hand side. 7, 8 or 7?
7, 8.
Only 7.
Do you think we need the 8? 8 is used. Equal or less than 8? This side. Right? Bigger than 8? This side. So we don't have to keep the 8 here. This one is only used for branching. So equal or less than here, this is the 7. And 12 goes to here. Then finalize. So in this case, the less than, I think I forgot the 3, right? Before that, I forgot the 2 promote the 3, right? So we need to go back. So here, so 3 should be, it was 7 and 8, right? Why is the 3 suddenly here?
It was 3.
3 already inserted, right? So that means 3 and 5 and 8, right? 3 and so this should be 3 8 because I forgot the 3 to promote. So this time we don't have to keep 3 and 5, both of them. Okay? Instead, we have only 3. Okay? 3, not this one. 3, 5, 8. Okay? Then the not 3 and 5. So we have 3, 5, 8 over here is a full. So including middle value, left hand side, going to left hand side? No. Instead, just left hand side, 3, and right hand side, and the middle value will be promoted. Reason is that this one is not used for the data pointer. This one is only used for the sibling pointer at the branching purpose. Okay, so this is the after we insert the 12. Okay. So what about the 9? Bigger than 5, bigger than 8, so 9 is supposed to be here, so we have space. What about 6? 6 is bigger than 5, less than 8, supposed to be here. Even though we have the space over here, we cannot insert. It will be messed up, all internal load. So we need to split. So 9, 12, 9, 12 is not changed. 9, 12, and the 6, 7, 8. So 6, 7, 8, this is the middle value. In the leaf node, including the middle value, 6 and 7. This is 8. And 7 will be copied to here. We have the space, 7, 8. So equal or less than 7, go to here, bigger than 7 and less than equal or less than 8 goes to here, bigger than 8 goes to here. This is the, then don't forget sibling pointer. Okay? What if 0 is inserted? Why don't you draw the index after inserting the 0? So most confused part is the internal load. Internal load, we are going to follow the same procedure as the B-tree index. Okay? However, leaf node, we need to keep the middle value because it has, we'd like to keep the all data pointer to the bottom, the leaf node. Okay, let's solve the problem together. 0, 1, 3. This is a 4. So which one is the middle value? 1. So including middle value, left hand side. The right hand side, 3. So we can split. And 0 and 1 here. And the 3 will be here. And the 1 is copied to the parent node. So 1 will be inserted. Yes, there is a room, 1, 3. Then after that, we can equal or less than 1. And bigger than 1 equal or less than 3 here. And bigger than 3 equal or less than 5 to here. Okay, this side will not be changing. Don't forget the sibling pointer. Like this one. One more. 13 is inserted. 13. What happened? Why don't you draw the one more? What is the result? We do not use any sibling pointer here because this internal load will be used for only for branching. Be careful this part, okay? So 13, where it goes? Which node? Most right hand side. So should be inserted, but it's a full. So 9, 12, 13. So we need to split. Equal middle value 12, 9, 12 is left hand side, and 13 will be right hand side. Then which one will be copied? The middle value 12 will be inserted to here. So it will be 7, 8, 12. Then we follow the promotion that is used for the B3. So 7, 8, 12. Which one is the middle value? 8 will be promoted. We have space. And 7, 12. We don't have to put the 8 here because it's only used for branching condition. Then check all the sibling pointer, especially this side. So bigger than 5 equal or less than 8 goes to here. Bigger than 8 goes to here. So no problem. And equal bigger than 5 equal or less than the 7 goes to here. And bigger than 7 equal or less than 8 goes to here. And 8 bigger than 8 equal or less than 12 and bigger than 12. And don't forget the sibling pointer. Then keep doing. Any questions? You are ready for the exam? Definitely the final exam. Okay, put your name and ID and submit it. It will be used for your extra point. Okay? Put your name and ID, then the submit it. Okay, so next, so actually, what if we delete the data? Delete the data. When we insert, in case of 4, we merge, either we split. It's the opposite. When we delete the data, nothing, we can merge it to the sibling node. So it's the opposite of the split and promotion. However, it's not that simple. So mostly removing the data from the B3 and B plus 3 is more complicated. I'm going to skip that part, but those who are interested, the merging, why don't you take a look at the textbook and ask a question if you have. So this is the end of the index. There is a second part of the chapter 17. I just realized that I do not upload the PPT file on Canvas, but I did the before class start, so you can take a look at. But we have the second part of the chapter 17, which is the practical database design and tuning. If we have a time at the end of the semester, we will cover quickly this part. So I'm going to skip right now. Then instead we are going to back to the chapter 14, which is the book. The normalization. Have you ever heard about the normalization? Database normalization. It's very important when you join any database related project, when you design and implement. So your project manager will ask, please normalize your database, okay? And apply the third normalization or BCNF normalization for your database design or up to the BCNF. So we are going to discuss about this normalization. By the way, in general, what does that mean, the normalization? In general, not for the database. when we are talking about the normalize. Why don't you normalize? And we need to normalize the data. What does that mean, normalization?
Reducing the data.
Using. So why don't you normalize your data? It's not fair. So we are going to normalize the midterm exam to the previous semester because the midterm exam was tough. So normalize. What does it mean, normalize? It's a kind of standardization. Okay? So if you are taking any data analytics or data mining class, you heard about the pre-processing. So before we analyze or before we process the data, we do something pre-processing. For example, so I'm going to decide the final, the grade. But sometimes the exam was difficult, but one of the students got the perfect, like the 100. So most of the students got the lower score, but because of one very excellent student, it's their variance difference. So we need to normalize, okay, standardize with the average and so on. So it's called the normalization. So we are going to apply the similar, not the same concept, but the similar concept to the database. In database concept, so we try to standardize our design. What is the criteria? What is the most important part when you design? So like in your page 1 and page 2, you design your database. What is the most important part of the design?
Relation.
Find the relational table, right? So what does that mean, each table? Think about the student table in the university database. Student table, student relation has only student information. And the instructor table has the only instructor information. Okay? Then, which means if we mix up the data, even the designing part is complicated. When I search the data, so where do I go to? We don't know. If I delete the data, like the student, it's one of the students dropped the course. But if I delete the data for the student in the mixed one, all data will be deleted sometime. So standardization means in the database is kind of no redundant information. It's very important to remove the redundancy. So think about the designing process, like the logical database design, the ER diagram. How do you find the entity? How did you find? By collecting all the entities that are same, right? Student A entity, student B entity, student 3 entity. By collecting such all student entity, we can define student entity type. It will be a student table, which means if I include the department information to the student entity, we cannot create the attribute. It's a different. So our goal of the database design is redundant-free database design. In other words, what happens when you have the redundant duplicate data in your database?
Updation or deletion.
Very complex. It's a mess up. Think about your student information is in the payroll, HR, international office, computer science department. What happened? You move in the new house. You need to update all of this. Very, very expensive. And to search, which database we need to search? HR or this one? It will be conflict. Also, so I don't want to spread out my information, all information into one room. Student, instructor, major, course, everything inside. Like I'm taking the Lee and the computer science, the main, everything is inside one record. What if those record is deleted? Sometimes your department will be deleted. So it's very, very difficult when you have the redundant information. So it's always database. Also, it's a waste of space and a lot of overhead. So it's a redundant free is our goal. So when we talk about the standardization of the database design, when we talk about the normalization, means normalization is the no redundant information. So we'd like to pursue. But it's not possible. It's just sometimes the idea to design the redundant free, 100% redundant free. It's the idea. It's not possible. So as much as, depending on the such a redundancy level, this is allow the redundant information, but limitedly remove the redundancy. And more strict redundancy. And the more strict the redundancy. And more strict the redundancy. Oh, opposite way. So sorry. So first, redundant information. That's called the zero normalization form. Zero normalization, no normalization. It's allow any redundancy. If you do not allow certain level of the redundancy, it's the first normalization form. First NF. If you apply the strict, more strict, it's the second normalization. If you apply the additional, the rule, it's the third normalization form. There's one guy, two guys, Bosch and the Code. Code is the Dr. E.F. Code. And his friend, the BCNF. They actually proposed another level of the redundancy. That's the BCNF. So BCNF is almost no redundancy. Zero NF is just a bag of information, just a collection of the information. So our goal is to get to the strict level of the normalization, which means no redundancy. Actually, this is not the 100% redundant free, but we can remove reasonably. Okay. Good news. I'm asking you, have you ever considered such the normalization process in the project? Probably not. We didn't cover that, but you already did your design. How? In nature, okay. No, if you believe you are the normal person, I'm not crazy. I'm not the stupid. Most of the normal people can imagine. It doesn't have to be database design, just organizing. So if I'm asking, why don't you organize your room? You don't want to mess up all the stuff together in one bag. Instead, this is database, this is operating system, also somebody, the alphabetical order. So if you believe you are a normal person, in general, people can do up to the third normalization automatically. And another good news is in the market, in real life system, in the real project, they require only little bit, one more step of the normalization. This is a BCNF, which means even though we do not know the normalization, we can do up to the almost 95% of the normalization automatically. Okay? Think about the idea of normalization is grouping by the same, so without redundancy. Like when you organize your table, when you organize your room or this room, you probably get together like the man and woman, or first the grade.